This lesson is on geometric series. Now this lesson builds off of geometric series that you should have learned back in Algebra 1. So in case you don't remember learning about geometric series in Algebra 1, you may want to go into my Algebra 1 section and look under the exponential functions. And at the end of the exponential functions unit, there is a video introducing geometric series. So that might be a good review in case you don't remember learning about these before. But you can still do today's lesson without this knowledge. It may just be good to refresh. So a geometric series is a series that has a common ratio. Basically what that means is you're multiplying by the same number over and over and over again. So if I look at this pattern here, I can see that 1 times 3 is 9. 1 times 3 was 3, 3 times 3 was 9, and 9 times 3 is 27. So this is a geometric sequence because it has a common ratio of 3. The formula for a geometric sequence is written up here. The formula for a geometric sequence is a to the n equals a to the 1 times r to the n minus 1 power, where a to the 1 is your initial, so your initial value, r is your common ratio, and n is going to be your term number that you're looking for. So this formula lets you find any number in the pattern. So if I wanted to write this geometric sequence in the formula, I would look and say my first number is 1 times my common ratio that we said was 3 to the n minus 1 power. And once I have that, I could find any term number I wanted in that pattern by just substituting it in there. So let's do a quick review to see which of these is a geometric series. So to find that, we have to see which ones have that common ratio. So a tip, in order to find this, since we know it's multiplying by some number every time, to find out what the number is here, we need to undo it and do division instead. So notice here it says divide the second term by the first term. So we would need to divide 1/4 divided by 1/2. And I know most of you have a calculator you can do this on, but in case you don't, it's never bad to review. Remember, division is multiplying by the reciprocal, so we flip these numbers, and that gives me 1/2. So that multiplied by 1/2. If I want to check it again, it says divide the third term by the second, so 1/8 divided by 1/4. That's the same as 1/8 times 4/1. And that again gives me 1/2. So I know this is a geometric series where my common ratio is 1/2. If I look at my next one, we can see right away there's a pattern, but this time, instead of it multiplying, I can see that it's adding the same each time. Anytime you add the same, that's called an arithmetic sequence. So that's not what we're looking for in this problem. Down here, I know to get from 1 to 1 would be times 1, but then that would be times 2. And then I can see that it's just not multiplying, so that one's also eliminated. So now let's try this one. Let's do 64 divided by negative 256. We can just write that as a fraction, because remember, division is the same thing as a fraction bar. And if we divide that, I know 8 goes into both of those. So let's divide both of those by 8. That gives me 8 over 32. which now I can see simplifies to negative 1/4. So from here to here, it multiplied by negative 1/4. If we try the next one, we have a negative 16 over 64. 16 goes into both of those, so that becomes negative 1/4. So I can see that this does have a common ratio, so it is geometric, and our ratio would equal negative 1/4. So this has just been a quick review of how to identify if something is geometric or not. So now let's go on to the new stuff. Now, we don't want to just be able to tell is something geometric or not. We want to be able to find the sum of all the terms in a geometric pattern. So that means if I had that initial one, 1, 3, 9, 27, they want us to now put a plus sign between it and add it all together. So the sum of this series would be 27 plus 9 plus 3 plus 1, which would equal 40. Now, if we have a short series like this, it's easy to just add them together. The problem occurs when we have a much longer one. Let's say we had 6, 7, 8, even 100 numbers long. We wouldn't want to have to find the pattern and list them all out. That's where this formula comes in. This formula says the sum of our series with however many numbers is equal to a sub 1 times 1 minus r to the n power over 1 minus r. And just like the original formula, our letters are still the same. A sub 1 stands for your initial term, r stands for the common ratio, and n is the number of terms. So let's try this in this formula now. If I wanted the sum of the first 4 terms of my pattern here, remember we said the first term was 1, and then 1 minus our rate is 3, and we're going to 4 terms over 1 minus 3. So if we simplify this in the calculator, we would first do our exponent, 3 to the 4th power, which is 81. So 1 times 1 minus 81 over, and let's go ahead and simplify this. That is negative 2. Now if I go in here, 1 minus 81 is negative 80. So now we have negative 80 over negative 2, which equals 40, which is what we added up before. So the formula still uses all the same numbers that we need. You just need your initial, your common ratio, and how many terms long it is, and then you just plug it in. The one thing you do have to remember though, using your PEMDAS, is exponents first. So let's try another one. This one, they tell us we want the first 6 terms of our geometric series. So if we fill in our information over here, our first term is 1. We don't know our common ratio yet, so we'll leave that blank, but we know we want n to be 6. And then if I take a look, I can see that my common ratio is each time it's multiplying by 4. That's the only information we need, and now we can solve. So we want the sum of the first 6 terms. That's equal to the initial term times 1 minus our common ratio to the power of how many terms we want, so 6, all over 1 minus our rate. So just like last time, we're going to do the exponent first. And since this is a times 1, we'll just ignore it. So we have 1 minus, and let's grab a calculator to find what 4 to the 6th power is. Ooh, 4,096 over 1 minus 4. So that gives us negative 4,095 over -3. And we'll stick that in our calculator. And we get that the sum of our first 6 terms is 1,365. And that would be your answer. So hopefully you're getting the hang of using this formula, because now we're going to practice using it in a real-world application. These are called Sierpinski triangles. And notice there's a pattern. And in this case, the pattern we're looking for is shaded triangles. So if we look, our first triangle is one big shaded triangle. Our second triangle has 3. Our third triangle has 1, 2, 3, 4, 5, 6, 7, 8, 9. And our last one, I can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9 groups of 3, which makes 27. So hopefully you've noticed, what's the common ratio here? Each time it multiplied by 3. So that means our common ratio is 3. And they tell us if we were to use our formula from the last page and added all these up, there's a total of 40 triangles in the first 4. But now they want to know which one of these formulas is the correct one to find the first 10. So if you need to go back, look in your notes. It's S sub n, our initial, times 1 minus r to the n over 1 minus r. So since they want the 10th term, that's S sub 10. Our first term again was 1. And no, it's not always going to be 1, so don't always assume that. Our rate we know was 3. They want the 10th triangle, so we'll put a 10 over 1 minus 3. Now, we got the top part matching in all of these, but let's simplify the bottom. S sub 10 equals 1 minus 3 to the 10 over 1 minus 3 is -2. So that means this is our formula. And now they want us to go ahead and solve this. Hopefully it doesn't explode your calculator, because 3 to the 10th might be kind of big. It is 1 minus 59,049 all over -2. So let's do 1 minus. That is going to give you -59,048 divided by the -2. And that gives you a crazy answer of 29,524 triangles. That is insane. You definitely would not want to continue the pattern and then add everything up. We just want to use the formula. So one more time we're going to do the sum just to make sure it's drilled in your head. Here's our equation. First thing we have to do is identify our first term and our ratio. We know the first term is always the first number they give us, so -256. And our common ratio is always what's in parentheses, so that means it's multiplying by -1/4. And that's all the info we need, so now we can find the sum. And now they want the first 17 terms. So the sum is equal to -256 times 1 minus a -1/4 to the 17th power all over 1 minus -1/4. So this might be a problem that you want to just go ahead and stick into Desmos, your calculator that's built into your program. And if we do that, it'll do all the work for us. A little hint in Desmos, anytime you want to hit a fraction, hit the division sign. So we have negative 256 times 1 minus, I'll put a parentheses, negative 1/4 to the 17th power. Close all of our parentheses, over 1 minus negative 1/4. And when we do that, we end up getting an answer that is about negative 204.8, but it says approximate to the nearest tenth, so I think we're good there. So negative 204.8. Now the next thing is using sigma notation. Now sigma notation is just another way of writing our terms. So this symbol here, the sigma symbol, that is a summation sign. That means you're going to add all the terms. Then we have our index, which is n. And then this is our lower limit. So that means our first term in this problem is 1. And then our upper limit here is going to be whatever the highest one is that they want. So 5, 10, however many terms long it is. And then this is your rule. So if we look at an actual problem using this, now they tell us it's the same formula, but now they tell us that we're not going to start at 1, we're going to start at 2. So our very first n that we plug in here is going to be 2, and then we're going to go all the way up to 5. So what they did is they used the rule. This was n equals 2, n equals 3, n equals 4, and n equals 5. And then they simplified it, and then you could actually go ahead and solve it. So there's no cool trick this time to add them together. We have to actually use this rule each time till we get to our upper limit. Then we're going to have to go ahead and solve each one and add it together. And that's another good time to use Desmos. Just plug it in all at once and it'll give you the answer. So here is our summation. And they want to know which one of these represents this answer. So our rule is 1/2, that was the initial number, times 1/2 to the n minus 1. So it tells us that we're starting at 1 and we're going to 3. So we have to do 1/2 times 1/2 to the 1 minus 1 plus 1/2 times 1/2 to the 2 minus 1, because that's our next term, plus 1/2 times 1/2 to the 3 minus 1, because 3 was our upper limit. So now if we simplify, that gives us 1/2 times 1/2 to the 0 power. Hopefully you remember that anything to the 0 power is 1. So that means that's 1/2. Now let's do the same for this one. 1/2 times 1/2, 2 minus 1 is 1. So that's 1/2 times 1/2. So that gives us 1/4. And then 1/2 times 1/2 to the second power. That gives us 1/2 times 1/4, which gives us 1/8. So that means this guy is our answer. So when we have to use sigma notation, we have to write this exact formula for each value of n, from the starting one to the ending one. Now this problem is a little bit trickier. This is a savings account problem. It tells you that each year on your birthday, you are depositing $200 into an account. And that account pays 4% interest compounded annually. And they want to know how much will be in your account after 20 years. So we need to come up with a rule. We know that your initial value when you're starting is 200. Then the rate each year, it gives you 4% interest annually. So we can't just put 4, we have to put 1.04 because you're still keeping the original amount you had, that's the 1, but then we're adding an additional 4%. And then our N is 20 years. So for this problem, we wouldn't want to use our summation formula because since N is 20, that means we would have 20 terms long. We don't want to do that, so we're going to go back to our original formula for summation. So 200 times 1 minus 1.04. We're doing this 20 years all over 1 minus 1.04. So this is another good one to just plug straight into Desmos. Try and find a way so I can see both my screen and that. So I'm starting with my division. 200 times 1 minus 1.04 to the 20th power, because it's 20 years, all over 1 minus 1.04. And that gives us a total of 5955.62. So if that's all you're putting in every year, after 20 years, you'll have $5,955.62 in your account. The last thing you have to be able to do is you have to be able to find the sum of an infinite series. Remember, infinite means it goes on forever. Now, there's one slight problem. Depending on the rate, or your rate of change, you may or may not be able to actually find an answer. So if you look over here, we've taken our rule, but now we've added these two parts to it. If the absolute value of your rate is less than 1, meaning it's a fraction, and by fraction it needs to be a proper fraction. It can't be improper because then it's greater than 1. Then that means the series converges to S. What converges means is basically the more and more terms that we add, the closer you're going to get to your answer of S. So if you put in 10 terms, and then put in 100 terms, and then put in 1,000 terms, the bigger you make this number, the closer it's going to get to S. So we can approximate the sum of an infinite series by putting in a big number like 100 or 1,000 in for n, and you can solve. If your rate is greater than 1 though, and remember it's absolute value, so if it's a -2, that's still greater than 1, then the series diverges. And what that means is your series isn't going to approach this number, meaning you can't find the sum. So you need to make sure you put in your notes that if it's an infinite series, meaning it goes on forever, then you can only find the sum if it converges, meaning if the rate is a proper fraction. As soon as you see a rate greater than 1, you automatically know you can't solve that problem. So we have one last example that shows this. So an infinite geometric series converges if the common ratio is a proper fraction. So if I look, I'm looking for anything that converges. So 4 over 3 doesn't work because that is 1 1/3. That's an improper fraction. So that can't work. Negative 2/3 works because remember we have to take the absolute value, and that is less than 1, so that works. 2 is greater than 1, so that diverges. And 3/4 is a proper fraction, so that also works. So this says find the sum of the infinite series. So first thing I need to look and see, is it convergent? Meaning, remember, is the absolute value of r less than 1? And r is always our part in parentheses. So I have negative 1/5. Absolute value is 1/5. And that is less than 1. So that means I can solve it. So since I can solve it, we're going to go ahead and we're going to go back to our sum formula. And we're going to use 1,000. So we know our initial amount is 32 times 1 minus negative 1/5 to the 1,000 power all over 1 minus negative 1/5. So we're definitely going to go back to Desmos on this one. And we'll type it in. 32 times 1 minus negative 1/5 to the 1,000th power, which seems huge, all over 1 minus negative 1/5. And when we do that, it gives us a value of 26.67. So we just have to see which one of these is the same as 26.67. But hopefully you know by now that anything that ends in 0.67 is some sort of fraction over 3. So that means this guy is going to be your answer. So remember, the key with infinite is first, is it convergent? And then when you go to solve the problem, go ahead and use a big number like 100, 500, or 1,000 to get an approximation for your answer. So I hope this video has helped you. Thanks for watching.